All right, let's do this. I've been putting this lecture off for a little while. It's a big one. Today we're going to talk about how standing waves create the harmonic series. The harmonic series are the frequencies that you hear when you play a musical instrument, and the secret to Western music is inside of that. When I say Western music, I mean music that's based on the scale that you hear when you play the keys on a piano. So, first of all, if we talk about musical instruments, those musical instruments that have pitch, so we're going to leave percussion instruments out of this, although there is some crossover. Percussion instruments, some of them do have pitch. Um, but we generally think of two classes of instrument, those that create their sound with strings and those that use some sort of wind blowing or vibration in a wind call or air column to create their um, music. So we're going to start with a stringed instrument here, and I've drawn a picture of a guitar with one string. Um, and so if you look at a guitar, you'll notice that the string is confined on either end. At the low end, there's a device called the bridge, and that holds the string in place so it can't move. That means it must be a node. And at the top of the area where you place your fingers, there is another little area where the string is confined, and that's called a nut, and that has to be a node. And the area in between is where the string can vibrate. And in the case of a guitar, that vibration is picked up by either a hollow box with a hole cut in it, or by an electromagnetic pickup, and then amplified so that it can be louder than the sound of just a string vibrating in one place. So we have to kind of analyze this and say what's really going on here. Well, we have definitely a length issue. And in fact, many stringed instruments, we control more than just the length by putting it in between this nut and this bridge. Sometimes you actually place your finger. I'm going to draw a picture of a finger here. You place your finger on top of the string at some place, and that finger acts like the nut does, and the string now has a different length where it can vibrate. So the length is the main thing that we change. The other thing we change about these strings is we do change the tension that they're under. In fact, if you ever play guitar or tune a piano, you know that there are some devices up here that allow you to turn a crank and make the string really tight and really loose, and that changes the pitch as well. And the third thing we do to change the pitch is we change the density of the string. And if you've ever played a musical instrument that has more than one string on it, you know that the strings that make the lower pitches are actually thicker strings made of more material. So those are the three things we can change. And I want to show you how these three things, in particular length, can change the frequency that you're going to hear, and also what frequencies, plural, you hear when you strike a string. So to begin with, we're going to do three things. What we're going to do is we're going to draw a picture, and on the picture, we're going to show our boundary conditions. Then we're going to set some sort of relationship between the length of the string and the wavelength of the wave that is going to be set up on the string when you pluck the string. Then from the wavelength, we are going to go ahead and figure out a relationship to get the frequency. And once we have this frequency, we're going to see if there's a pattern, and maybe we can predict what's going on here. And so buckle your seatbelts. This is going to be kind of interesting, and I've never done it on this format with this kind of paper before. And so let's get this going. All right, here we go. So the very first and simplest wave you can have, if you have a node on each end, and I'll write node here and node here, is that you could have a string whose normal position is here, and it's going to vibrate out this way, and of course also this way. It's going to vibrate back and forth. And so this is the length of the string right here. But the question is, what is the relationship between the length of the string and the wavelength? Well, this hump right here, this is a one hump out of a cosine or sine wave. I guess sine would be the best choice here. And so this is really half a wavelength. Okay, that's not what I meant to do. I meant for this to be a 2. Look at that. Look how carefully I turned that L into a 2. So this is half a wavelength going on this. So the length of the thing is half a wavelength. Now, what we're going to do is we're going to reverse this, and we're going to say the wavelength is twice the length in this situation. And the reason why we do that is we're going to put this into the velocity equation, or the wave equation, v equals lambda f. And so we're going to replace this lambda with 2L. So v equals 2LF. And that means that f, for this situation, is going to be V over 2L. And this is the simplest thing we can do, so I'm going to make this F1, the lowest frequency. Now, the lowest frequency is called the first harmonic, because all of these are going to be called harmonics, but it's also called the fundamental. The fundamental frequency is the lowest frequency you can create. It also happens to be, in most cases, the loudest thing you're going to hear. And your ear actually thinks of this as the note name, the actual pitch. So this is a very important wave that fits on a guitar string or a harp string or a violin or anything like that. What's the next most complicated thing we could do? Well, we still have to have a node at each end. And there's where the string would be if it wasn't being vibrated. But now we're going to have a wave that has an extra node in the middle. And of course, that's the length of the string. And in this case, the length of the string is exactly equal to lambda. Okay, that means when we take our formula, V equals lambda F, we can just put in V equals L times F. And that means that F2 is V over L. This is called the second harmonic. It's also called an overtone. Now, one thing you may notice, and this is some musical terminology, you may notice that this frequency here and this frequency here are one is half as big as the other. In other words, the first overtone, the second harmonic, is twice the frequency of the first harmonic. Doubling the frequency in the world of music is called doubling the frequency in music is called an octave. And it has the same note name as it did before. In other words, if this was a C, like middle C, this would also be a C. This would be the C above middle C. And they have the same musical function, but one sounds higher than the other. So that's one octave higher. What's the next most complicated thing you can do? Well, all right. Now we've got a node at each end. And now we're going to have oh, that's a delicious drawing, Harmon. Now we're going to have two extra nodes in the middle, and that's the length of the string. Therefore, the length of the string is going to be equal to 3/2 of a wavelength. And we kind of did this before the other day. Now we can put that in. That says that lambda is 2/3 L, and V equals 2/3 L times F, or F3 equals 3/2 V over L. This, of course, would be called the third harmonic, etc. Or the second overtone if you wanted to get into this. Now, I want you to notice that this fraction that we came up with here showed up again over here. So we really could predict what the rest of these are going to look like. In fact, we could predict them based on our intelligence. If we made a list of all the frequencies, we would write that this was V over 2L, V over L, 3V over 2L, and the question is, what are the next two? You can work it out from geometry, or you can just look at this pattern, and in fact, it helps a little bit to put them over a common denominator, to put this over 2V over 2L, where the 2's would cancel, and now they're all over 2L, so I guess this would be 4V over 2L and 5V over 2L, etc., etc., etc. So we could come up with a formula that works forever and says that the frequencies that you get on a string are equal to n times V over 2L. And this is the harmonic series for a string. N is the number of the harmonic, 1 for the first harmonic or fundamental, 2 for the second harmonic, 3 for the third harmonic. V is the speed of the wave on the string, and L is the length of the string. And now let me transcribe this over here. And we can see that the shorter the string, if you drop the length of the string by putting your finger, say, on a guitar fingerboard or violin fingerboard and shortening the string, then what's going to happen is the frequency is going to go up. You're going to get a higher pitched note. That is the main way in which this works. And the note name comes from putting n equals 1 in here. That is typically what you put in there. But let's have a look at this V, because remember, there were two other factors that affect the pitch that a string makes. And V is the speed of waves on the string. And that's difficult. It's determined by the medium. And it turns out that one model of the speed of waves on a string says that the speed will be faster if the tension in the string is higher, and the speed will be slower if the density is higher. This is the tension over the density. So you can see that we also could change the frequency that you hear by changing the tension and the density of the string. Now, these two are not normally changed on the fly, with the exception of a broomstick bass, which is a rural American instrument from the way back that I've only ever seen in cartoons. So anyway, so they're all three things: the length, the tension, and the density are in here, with the length being the one that you change in a musical sense to change the frequencies. One more thing about this that is kind of fun, and that is we said that between the first harmonic and the second harmonic, that this was a doubling of the frequency. Is this a tripling of the frequency? Well, it is. It's a tripling of the original frequency, but that's not another octave, because to be another octave, we would have to be doubling this frequency. It would have to be 2V over L. And that doesn't happen until you get to the fourth one. So if this was the note name C, this would also be a C an octave higher. This one, however, turns out to be a G. And then this one is also a C, even higher than that. And then it starts going crazy. And if you watch that video that I left for you, What's Up with Noises, she worked out what all these are. But what I wanted to point out is that inside of every note played on a stringed instrument that is a C, there is a G hiding. That means the G and C sound good together. There's also an F hiding in there somewhere, I think, and some other notes. You can get them all in there. But as it turns out, the higher you go in the harmonic series, the quieter the sound is from that particular frequency. So really, this one is the major one. So let's cross that out. So there's a G hiding inside of every C. That means that G and C sound good together. When you play a G with a C, then the G kind of reinforces or resonates with the G that's inside the C, and they sound good together. So this is what makes Western music sound the way it does, is the notes are all hidden inside of each other and sound sometimes good, sometimes bad when played together. Okay, so that's a lot to digest, but I think we need to go a little further, and I think we'll do that in tomorrow's lesson on wind instruments. So thank you so much for your patience.